A very good evening to Dr. Shakina and Dr. Rasita. So we are from Group 15, Content Methanol Production. So we would like to present our presentation today. So first I would like to start with the block flow diagram. So in this block flow diagram, first we have four reactors, which is autothermal reformer, methanol converter, flash, and distillation column. Autothermal reformer, the temperature is 800, pressure is 1. Methanol converter is 210 and 15 bar. Flash 150 degrees Celsius and 22 bar. Distillation column is 110 degrees Celsius and 2 bar. And in total we have 9 streams. Start with stream 1 natural gas and ending with our product, which is methanol. Yeah, methanol. Stream 3 is added to autothermal reformer, and stream 2 is actually absorption. It's not an outlet. And stream 6 and stream 7 is to waste recovery. Then this is our process flow diagram. Our process flow diagram is this one, where we have the reactors over here and here, and this is the flash tank, and this is distillation column. So we have 9 streams in total, and we have heater and valve, cooler tank, and compressor as well. And I have included the temperature and pressure for each stream. Together with that, we have material balance calculation, where we have counted it for last sem.
Assalamualaikum, hi and good evening to all doctors. Okay, my name is Nujah Najwa. Today I'm going to talk about our first reactor, which is autothermal reformer. So in this autothermal reformer, we put a heater in each inlet stream, which is natural gas stream and oxygen stream. So our first heater is in natural gas stream. So it goes in and it goes out with same mole, same bar but different in temperature. So basically heater is to increase the temperature. So here it increase the 500 Celsius to 800 Celsius. So um, as you can see, the inlet energy calculation. So then I calculate all the CP and all the data H for each substances for inlet and outlet energy. So then after that we multiply with the data H with the mole itself. So then we got the total inlet energy and the total outlet energy. So then when the total outlet energy is minus with inlet energy, we got the total heat in kilowatt, which is around 4 million kilowatt. So then moving on to the second heater, it's same with first heater, but this one in oxygen stream. So it's just the same. It wants to increase the temperature, which is from 500 to 800. So basically the pressure is the same. So then we calculate the inlet energy and the outlet energy. So yes, we got the total heat, which is around 2 million. So this is just the conversion of heat Q if you want to see. So then the two inlet stream will then go to the our autothermal reformer. So basically autothermal reformer have 4 streams, two inlet stream and 2 outlet stream. So the 2 outlet stream is just now is being already high in temperature, which is 500, which is 800. Then it will increase to from 800 to 850, and also with different and also with different pressure, which is from 1.5 bar to 1 bar. So basically we calculate it, inlet energy calculation just the same. We calculate the CP and then divide it, we then multiply it with mole, with their mole. So this is our energy and inlet energy. So then when we total up, we use the same formula. So then we got this is the value for total outlet energy and this for total inlet energy. So then we calculate the total heat Q in kilowatt. So we got this value, which is negative 683039267.2, which is exothermic.
Okay, so now next I'll start with cooler. Okay, after autothermal reformer, we have to decrease the temperature, so that's why I use a cooler. Coolers to decrease the temperature from 850 to 200 degrees Celsius. Um, so I've calculated the energy balance. So this is my table for inlet and outlet energy. Um, on my left hand side is the calculation for inlet, and my right hand side is calculation for outlet. Mm, yeah. So since most of it is gas, so we can take the data from table B8 and a few which is methane, inert and ethane, we take it from table B2. So as for the final calculation, NH out minus NH in, and for the unit conversion we have after unit conversion around 14 million kilowatt is obtained. And for the energy balance calculation, since there's no kinetic elevation and work shaft, so H equals to Q, where Q equals to 14, negative 14 million kilowatt. The next one is compressor. Compressor is to increase the pressure. So this is the working for mechanical energy balance. So my work shaft, I got it for 1.6 times 10 to the power of 11 joule. The pressure increased is from 1 atm to 15 atm. The next one is my reactor. My reactor is methanol converter to produce methanol. So my energy balance is same as for cooler, inlet minus outlet, outlet minus inlet. So this is the table for inlet and outlet. So on my left hand side is calculation for inlet, and my right hand side is the calculation for outlet. And we have used certain formulas, which is for pressure change, temperature change over here, and after that we have to use the final calculation as well unit conversion also. So after unit conversion we get around 3 million of kilowatt of heat energy. And for the energy balance calculation, since there's no kinetic elevation and work shaft, so H equals to Q, where Q equals to 3 million kilowatt.
Assalamualaikum and a very good evening to Dr. Azita and Dr. Shakina. So today I'm going to talk about compressor. So for this compressor, the function of this compressor is to increase the pressure, which is from 15 atm to 22 atm. And then in order to calculate the work shaft, which is the mechanical energy balance, we're going to use this formula. And then the work shaft is 83 million 83,829,535,337.24 kilojoules. Okay, so now we're going to move on to flash. So for our flash, all of our references are based on table B2, and then the and then we calculate the H by using table B2, and since the gas is your gas, so we are going to use the change in pressure by using AN plus 3 BN over T square times by change of pressure formula. So after we times all the number of mole times with the enthalpy, after we substitute into this equation, we get 5,414,579.47 kilowatt. So okay, we also is we also assume that the Cp for liquid is the same as the Cp for the gas. This one. Okay, now we are going to move on to distillation column. Okay, for distillation column, all of the references are from table B2 and table B8. And then for distillation column, only water and methanol is calculated since all of the impurities are absorbed in water. Okay, and then we calculate the change in temperature by using Cp dt and change in pressure by using the AN plus 3Bn formula. This one, AN plus 3Bn over T squared times with change of pressure formula. After we substitute all of the values into the equation, we get all of these value, and then the Q for this reactor is negative 1849042.14 kilowatt. Okay. By the way, this distillation column is to purify methanol.
So that is all for the whole reacting process. So now I would like to go for the costing. So this one is actually the costing for electricity. So based on the references, this table is got from the TNB website, Naga National Berhad. So as we see for industrial tariff, we have four, but we have to take the high voltage tariff because we are doing methanol production. And since the company is running for 24 hours for 330 days, which is like peak period, so that's why we take 33.70 cent kilowatt per hour. And yeah, and then as we see here, so first we have to um, gather all the Q, which is heat that is produced from all the reactor and unit and components and everything. And then those reactors which have negative values are not counted because it is neglected. Only the positive values of Q are obtained. And for compressor, both the compressor is work shaft, so nothing to do with Q. And everything we sum up and we times by our operating cost, which is 24 times 330, and we will get the pricing for costing of electricity.
This is the last part about costing. So as you can see, we calculate the cost for raw material, catalyst and utilities. So this is the cost. So for conversion, this is here, conversion. So then when we calculate all this, we get the total operating cost about 0.13 trillion. So when we calculate revenue minus operating cost, got we lost, our company is lost, we don't get any profits. So yes, this is our cash flow. It is decreasing because we don't get any profits for 20 years. So in 20 years. So that's all from us. Thank you.